Hey guys, and welcome back to my channel. Today we're going to talk about the Denavit-Hartenberg algorithm. And what is Denavit-Hartenberg and when do you use it? For example, if you're having a robot with a robotic arm, you want to know the position of your tool, maybe the pen, through these different joints to your base frame, for example, your shoulder. So there's different ways of calculating this. You usually do something called an homogeneous transformation matrix. And it basically says how much you have to rotate. So rotate and then translate to get to the position you want. And to do that, it might be a bit complicated, but there are different shortcuts that you can do to get to the same matrix. And Denavit-Hartenberg is one of them. So I'm really excited for you to check out this video. So Denavit-Hartenberg, it is a way to find the position of your robot's end factor relative. So what does this actually mean? So this means that there is a position that you would like to find. For example, let's say we have this robot here. It is very simple. It has one arm here, then it has here a revolute joint, then it has another arm, a joint, an arm, a joint, and then here we have this tooltip here. So this will be the frame, and this will be the end factor. So if you would think about this as an arm, you might say that the end factor is the finger and the base is your shoulder of this arm. Okay. So, as I said before, this is a way to find the homogeneous transformation matrix. So when you want to do a calculation from a base frame through the tip, you use homogeneous transformation matrix. And why do we do that? It's because the matrix is basically combined of two things. It's it's the rotation that is needed to do, and then there's the translation that is needed to do. Okay? Depends on how many joints you have. This will be the rotation translation put into one matrix. So why do we want to do that? It's because if you code a program that makes the different translations and rotations, you want the matrix that you multiply with to be the same size. Not rotating with one and then translating with another sized vector, okay? So this makes computation much easier. We want to do matrix multiplication when we code. So that's why we do this. So Denavit-Hartenberg is just one way to find this kind of homogeneous transformation matrix. So the question is now, how is that done? So in this Hartenberg model, it is actually fairly easy. So you check two consecutive links, which basically means that you compare this link to this link, and then you compare this link to this link, and then you compare this link to the end factor. Then you put all of them together in order to get the translation rotation that is needed. So the difference here will be one matrix, the difference here will be one matrix, and the difference here will be one matrix. Then you just multiply all of these different matrices to get the total change from this point until here. So how do we actually get this matrix? So we know now that we have to check the consecutive links. And how do we check? What does check actually mean? So what we do want to do is find 4 parameters. We have to find 4 parameters between each of these links. Okay, so which parameters do we need? We will need the parameters which is called A, alpha, D, and theta. And of course, these can be named differently depending on who's having the lecture, so just be aware of that. And this will be the distance, and D will also be a distance. And alpha and theta will be angles. So, where can we find these? So this will be between ZI and ZI minus 1. This will be the angle between ZI and ZI minus 1. And this will be the distance between XI and XI minus 1. And this will be the angle between XI and XI minus 1. So you might wonder why we don't have Y in here, just Z and X. It's because the rule that this is the Z-axis and this is the X-axis, and then you always know the Y-axis, so it's actually just an extra variable that you don't need in the calculations, because if you know where your Z and X is oriented, you will know where Y is. So that's why it's not interesting. Okay, so we know now that we want all of these. And then maybe we can do a quick little example that I hope will make it more intuitive for you, because you might not understand how to transform this into the matrix in the end. Okay, so let's take this example like we did before. Okay. So this is our robot arm, as we said. So what you want to do is that you want to point out our coordinate system in each of these frames. So we have Z, we have X here, and then we will have also a Y-axis. So there's different rules that we have to apply when we put this frame on these different joints, is that Z should always be in the direction of, here you can see that the revolute joints are basically spinning, and they usually spin counterclockwise. So we can see this is spinning like that, and this one will also be counterclockwise, so it will be spinning like that. The same with this one. Okay, and the rule is that you hold your thumb like this, and your fingers will be in the direction of the rotation, and your thumb will be in the direction of where the Z-axis are. So if we will basically hold the joint in our hand. Okay, so that means that here we know that we can call the joint 0. So we know that the joint 0 will have a Z-axis pointing upwards, because that's the rule. Okay, and the question now is where to put X. And this is actually pretty easy because it's arbitrary. You could put X in this direction, you could put X in another direction. It depends a little bit on you. Let's put it here for simplicity. And then we know that Z needs to be perpendicular, so it will be somewhere here. Okay. Another thing that is good to know is that you actually can put this point, so the point 0, 0, anywhere here on these z-axis. So since we're going to compare this joint to this joint, it is actually a little bit easier to just move it along here and put it here. It might not really make sense right now, and the answer to why we can do this is a bit complicated for this video, so just go with the flow and accept that we can move it along the z-axis. So I'm just going to put it up here, and you will see soon why this is actually helping us, okay? Oh, this is y0. So this is basically the same. This is for 0, our 0 joint. Good. So you understand the principle maybe of putting the coordinate frames everywhere. So we want to find all our angles A, alpha, D, and also the angle here for our frame 0, for frame 1, for frame 2, and then our tooltip. Okay, so the first one we actually checked to the base, and the distance between the base and our z is actually 0. If our z-axis would start here, there would actually be a distance between them, but they're on the same axis, okay? So the distance is 0 between z base and z0. Alpha is basically 0 as well, since we can see here that there's no, I mean, you don't have to rotate anything because they're on the same. The same for x, that would go straight here, straight there, no distance, and also no angle between them. No, sorry, no distance there. But we will add an angle, since it is a rotating revolute joint. So you will never rotate about the z-axis here, like automatically, but you do rotate against x, okay? So we have theta 1 there. And then we check next, which is our frame 0 against frame z1. So we have to put out z1, okay? So as the rule goes, we can see here that it's turning this way, okay? So we know that our z-axis has to be out from the paper, okay? So for simplicity, we start from the same point. So we point it outwards here. Here's our z1, okay? So it's basically where our y0 is our z1. And then we will point out where x is. And then we know with this rule that z needs to point upwards. Oh, sorry, that y needs to point upwards, okay? This is our y0. Okay, so now it's a little bit more interesting. So here we can see that the distance between z1 and z0 is basically 0 because it has not translated anything. So we continue writing a 0 here. Now we can see that there is indeed a rotation going on. So this is the angle between Z0 and Z1. And since in robotics, when you put a line like this, it means that it's perpendicular, that it goes out. It's as if this would basically just be a straight point out from the paper. So this means that it's 90 degrees angle. So we can write 90 degrees or P divided by 2. And then we see the distance between X, which is 0, and then the revolute joint gives always us an angle here. So this might be 0 when you use another joint that just moves forwards and backwards as a translation. Okay, let's check the third joint. So let's check the third joint. The same principle applies here. It rotates around and Z goes out. And we have X going up here. And we have Y going up here, okay? So now you can see what I talked about down here before. If the joint would have been maybe translated to the right, there would be a distance between them. Now there's also a distance between our first and second joint. So we actually put in now, we call it L1. So now it's getting a bit messy in this paper, but let's say that you can see here that this is L1, the distance between these two joints. So I have L1. We can also see that both Z2 and Z1 point out from the paper, so they are actually not rotated. The x-axis are also pointing the same direction and there's no distance between them. If there would have been distance between them, that should have been shown as if I just write this out from the top maybe. Right now you can see the joints like this. Okay, if that would have been the case, that we have maybe another way, sorry, it was a bad painting, but okay, if it would have been maybe like this, then you can see that there is maybe a movement between the x-axis. But now there is not. So we're still putting a 0 here. And then since we have the revolute joints, we will put. Now we come to the last part here. And we can also see that this is the same. There's no distance, no rotation here, no distance there. So as I said before, we want to create a homogeneous matrix that we can calculate with. So what we actually will do is that we will take link by link. So T is our final matrix when it goes from link 0 until link n, which is the end of the links. So this is our starting base and this is the tool position, okay? So this is what we want. So we will go through the first translation and rotation matrix, and then we take that times our translation and rotation matrix from joint 1 to 2, so the comparison between 0 and 1, the comparison between 0 and 2, then we continue like that until we are at n minus 1, t compared to n. So basically the last one. Okay? So we just multiply them over each other to get our final matrix. And how do we do that then? So a t, so 1ti minus 1 until I is the same as our rotation with alpha that we had times the translation of A that we got times the rotation with theta times the translation of D. So D, theta, alpha, no, A and alpha that we just got, we basically put in. So how do these look like? Alpha and theta here will be against the x-axis, and theta and the D will be on the z-axis. So just to show you here, first we can do the Rx, okay? Which basically is a rotation on the x-axis, so that's why that axis is still. So it's 1, 0, 0, 0. And then we have 0 cosinus of alpha minus sine of alpha and 0. Then we have 0 sinus of alpha and cosine of alpha. Then we have the translation matrix dx, which first basically is you multiply with the identity first on the rotation part because you just want to have it as it is. So if you would have 0 here and you multiply with the rotation matrix wouldn't exist anymore because you just zeroed it out. Okay? And then here we will have A. So that is the translation on the x-axis we do. So basically on the same way, the dz will also have the identity first. And then since it's on the z-axis, it will have d here on this row, okay? dz and dx. And then we have the rotation on the z-axis. Okay, so, okay, let's start. So it's cosine of theta minus sine of theta 0, 0, because there's no translation here, okay? Then we have sine of theta, cosine of theta 0, 0. Okay. So you basically multiply, you put in your values, multiply Rx times Dx times Rz times Dz to get the first T. So you can do that, and there's also a little smaller shortcut where all of that is already combined. We have cos of theta minus sine theta 0, and then we have A here. Then we have sine theta times cosine of alpha, and here we will have cosine of theta times cosine of alpha, and here we will have minus the sinus of alpha, alpha, and here we will have, I don't know if I maybe did this a little bit too big, minus sine of alpha times D, okay? And then on this third row, we will have sinus of theta, sinus of alpha. Then we have cos theta sin times sinus of alpha. And then here we will have the cosinus of alpha. And here we will have the cosinus of alpha times d. Then here it will be 0, 0, 0, 1. So this is our final matrix that we use. So this matrix is basically our t n minus 1 to n. So instead of multiplying all of these after each other, you can just use this one for every comparison of the joins. And then you multiply all of these different t's with each other, and you will get the homogeneous transformation matrix. So that is basically how you do the Denavit-Hartenberg, where you find the position of your robotic end factor relative to the base frame. Thank you so much for watching. Give it a thumbs up and don't forget to subscribe down below. I post videos about machine learning, computer vision, robotics, so stay tuned. And if you want, check out my Instagram account Kixcodes, where I post the same content as well. So bye and see you in the next video.